Hi everyone, Ross Satchell from Microchip back again. In the previous video in this series, we toggled the onboard user LED every 1 second by polling the interrupt status flag of timer counter A. In this video, we will toggle the onboard LED purely with interrupts. This means we won't need any logic code to decide when to toggle the LED, as it will be done completely by hardware peripherals. In this project, we will also use Configuration Change Protection, or CCP, registers to output our peripheral clock so we can confirm it is what we expect. This is a very useful sanity check when starting a project. Now, the first question you're probably asking is, why would I want to do that? The answer is, we can then use the CPU to do other things, or even put it in a lower power mode, also known as a sleep mode. These sleep modes are especially useful for battery-powered applications, such as Internet of Things applications that are required to use as little power as possible so that they can run potentially for years on a single battery. To illustrate this, in the next video in this series, we will use a bench multimeter to measure the current consumption of this project in different sleep modes, as well as the current consumption of the project in the previous video so that we can compare them directly. So let's get started. Start by connecting your AT Tiny 1627 to your host computer and create a new bare metal project. If you have issues with a kit window not appearing, please refer to video 1 in this series. If you can't remember how to create a new bare metal project and main.c file, please refer to video 2 in this series. Before we start getting into setting up timer counter A or the sleep controller, we will set up the configuration change or CCP registers. CCP registers were introduced in the first video in this series, so if you're unsure what they are, please refer to that first video. They are also covered in the tech brief TB3262, Getting Started with Writing C Code for AVR MCUs, which is linked below. I recommend you either bookmark the link or save the PDF somewhere handy. So in TB3262, if we revisit section 1.5, it tells us there are 2 types of writes to a protected register, each with its own key. There's protected I/O registers with the key IOReg, and protected self-programming registers with the key SPM. The table in section 1.5 shows some of the registers that are covered by configuration change protection. The first entry shows if we want to select the clock source and output the clock, we want the clock control register, main clock control A, which uses the IOReg key. Then, if we open section 3 of TB3262, we can see subsection 3.5 is writing to CCP registers. So let's open that. It starts by telling us that attempting to write to a CCP register without following the correct unlock sequence leaves the register unchanged. It then shows one method of writing to a CCP register but has a note underneath stating that this is not the recommended way of doing this. Instead, to write to CCP registers, after writing the signature to the CCP register, the software must write the desired data to the protected register within 4 instructions. To meet the timing requirements, these writes are often handled by assembly code. It then shows 2 ways of correctly performing these writes. I will be doing the second one, which uses macros, making it easy to understand what's happening. To use these macros, we need to include the header AVR/xmega.h. Then we can write to the protected registers using the command _protected_write, then the register name, then the macro for the configuration. Now, before we jump over to MPLABX to set that up, we need to figure out which registers we need to write to. In the Tiny2 datasheet, in section 11, Clock Control, let's open the functional description. There's a figure showing the main clock and prescaler with several different oscillators gated by a multiplexer that then feed into a main clock prescaler. There's a note below that which reiterates what we just read in the tech brief TB3262. Let's jump to the register summary. So there's main clock control A, which allows us to select our clock source and to also output the system clock. As I mentioned earlier, this is very useful as an early sanity check, as we can be sure the clock source is what we expect. So we want the 20 MHz oscillator and the clock out in main clock control A. Then on to main clock control B. There is the prescaler division and the prescaler enable. I will be setting the clock to the same frequency as our previous videos, which was 3.333333 MHz. To get that frequency with a 20 MHz oscillator, we need the prescaler to be 6. That is, 20 MHz divided by 6 equals 3.333333 MHz. Now we have enough to set up the clock. Jumping back to MPLABX, first I will include AVR/xmega.h as outlined in the tech brief. Next, I'm going to create a function that takes no parameters, has a void return, and call it main clock control. Now in the function, I will call the _protected_right function and pass it first main clock control A and then the settings that I wanted. The first one was clock control and the bit field was clock select, and then the setting was OSC20M. So that is the name of the relevant macro. I can then use the OR operator and select the second setting for main clock control A, which is register clock control and setting clock out. Again, that is the name of the relevant macro bit mask. Now on to main clock control B, in which the register is clock control, the bit field is PDIV, and the setting is 6x. The other setting was enabling the prescaler, in which the register is clock control and the setting is PEN for prescaler enable. Since I put my main clock control function after the main function, I will need a forward declaration, also known as a function prototype. Then inside the main function, I will call my main clock control function. Now build and program the device, and I will connect my logic analyzer to the clock out pin. But how do I know which pin is the clock out pin? Jumping back to the datasheet, Section 3, I/O multiplexing and considerations. In Table 1, if I look at the columns labelled Other/Special, I can see that clock out is on pin PB5. Once I connect my logic analyzer to pin PB5 and also connect ground and then take a sample, I can see the clock out has a frequency of 3.333 MHz, which is exactly what I was expecting. Now we can be sure that any peripherals using the main clock will operate as expected. Now let's start setting up our other peripherals. While there are a few different ways to do this, including the real-time counter or the watchdog timer, I'm going to use timer counter A again. This is primarily to be consistent with the previous episode. We are going to spend some time in the TCA section as well as the sleep controller section of the datasheet. Let's start with TCA since we're already somewhat familiar with it. So open your datasheet to section 21, timer counter A, and in the menu on the left, let's go to the functional description. We can see some things that were covered in the last video, like the definitions, initialization, operation, and interrupts. While we will need those again, the thing I'm looking for now is sleep mode operation. So let's click on that. It tells us that TCA is by default disabled in standby sleep mode and that it will be halted as soon as the sleep mode is entered. However, the module can stay fully operation in standby sleep mode if the run standby bit in the TCA Control A register has a 1 written to it. It also tells us that all operations will be halted in power down sleep mode. Since this time we won't be counting the number of times a 1 millisecond interrupt has occurred, we need to figure out how we will make the onboard LED toggle every 1 second. Since we know the peripheral clock is 3.333333 MHz, then the period is the inverse of that, which, as we found in a previous video, was 300 nanoseconds. I am going to use a prescaler to slow down TCA a bit. I've decided to use the maximum prescaler of 1024. So then, 300 nanoseconds multiplied by 1024 equals 307.2 microseconds. Now we just need to figure out how many times 307.2 microseconds goes into 1 second. The answer is 3255.2. But since we need to use an integer, let's just truncate that to 3255. So jumping back to MPLABX, I will create another function, this one called initTCA, which takes no parameters and has a void return. In it, we will set up TCA. In the Control B register, we will be using the waveform generation normal mode, and then in the int control register, we will also be enabling the overflow interrupt. Both of these are just like we did in the last video. Then we set the period like we did last time, except now the value we use is our new calculated value of 3255. The last thing to do is in Control A register, we need to select our prescaler of 1024, enable the timer, and set the run standby bit so that it will operate in the standby sleep mode. Now we have set up TCA, let's set up our LED pin as an output. I will create a function called initPorts that takes no parameters and has a void return. Since the LED is on pin PB7, we will just set the port B direction register using the pin 7 bit mask macro, just like we did in the previous 2 episodes. Now we need to set up the sleep controller. Let's jump back to the datasheet, this time to section 12, Sleep Controller. In the overview, it explains that sleep modes are used to shut down peripherals and clock domains to save power. The sleep controller controls and handles the transitions between active and sleep modes. We have 4 modes available to us. The first is active mode, where our software is executed normally. Then we have 3 sleep modes. They are idle, standby, and power down. We will dive into those a bit more in a moment. All sleep modes can be entered into from the active mode, then interrupts are used to wake the device from sleep and return to active mode. The available interrupts depend on the sleep mode used, so we will need to take a look at the sleep modes to figure out which we can use with timer counter A. When in sleep and an interrupt occurs, the device wakes up and executes the interrupt service routine, or ISR, and then returns to normal program execution from the first instruction after the sleep instruction. Also, any reset will take the device out of sleep mode. The contents of the register file, SRAM, and registers remains intact during sleep. Then we have a block diagram that helps visualize sleep. Sleep control sends the sleep state to both the CPU and peripheral. Then the sleep instruction is sent from the CPU to sleep control. The interrupt request is sent from the peripheral to the CPU to return to normal code execution. Then in the functional description, we have instructions on how to initialize sleep. First, we configure and enable the interrupts so that they will wake the device from sleep. Also, enable the global interrupts. Second, select which sleep mode to enter, enable the sleep controller by writing the sleep mode or S mode bit field, as well as the sleep enable SEN bit in the Control A register of the sleep control module. Finally, issue the sleep instruction and put the device to sleep. There's an important warning there to make sure we understand that if we put the device to sleep without enabling interrupts, then the device cannot wake up again. At that point, only a reset will allow device operation to continue. Now we have the different sleep modes. Idle, in which the CPU stops executing code which reduces power consumption. All of our peripherals are left running and all interrupt sources can wake the device. Next is standby, in which all high-frequency clocks are stopped except for any peripheral or clock that has been enabled to run in standby mode. And as we saw when going over TCA, we can enable that with the run standby bit. In this mode, the power consumption is dependent on the enable functionality, and a subset of the interrupt sources can be used to wake the device. Finally, there is power down, which is the deepest sleep mode. All high-frequency clocks are stopped, and a subset of peripherals are running, and a subset of interrupt sources can wake the device. Then in Table 12-1, we can see the various clocks and peripherals, and whether they are active in the different sleep modes. TCA uses the peripheral clock and is active in idle mode. It's active in standby mode provided we set the run standby bit of the corresponding peripheral, which in this case is TCA. TCA is not active in power down mode. Then jumping to Table 12-3, we can see the TCA interrupts are active in idle mode, they are active in standby mode, provided we set the run standby bit of the corresponding peripheral, which again is TCA. Next is the wake-up times. We can see the normal wake-up time is 6 peripheral clock cycles, plus the time it takes to wake the main clock source and the time to start the regulator if it's been switched off. There are some notes that in idle sleep mode, the main clock source is kept running, so we would just be looking at 6 peripheral clock cycles. Then in standby mode, it would be the 6 peripheral clock cycles plus the oscillator startup time. Now let's go through the sleep control registers to see exactly what we need to set. There's just one register, which is Control A. We want to set it to standby, which is the deepest sleep that we can use while still having TCA use interrupt-based wake-ups. Then we want to set the sleep enable bit. So I'm going to create a function called initSleep, which takes no parameters and has a void return. In it, we just write to the sleep control register, Control A, and we set it to sleep control, S mode, standby group configuration. Then we can OR that with sleep control, sleep enable bit mask. Before we forget, we need to add function prototypes for those, just as we did for our main clock control function. Now we need an interrupt service routine. The nomenclature for writing one is ISR, and then in parenthesis, the interrupt vector. To find the name of the interrupt vector for TCA overflow, we can jump back to the datasheet. Section 8, Peripherals and Architecture. Just under that in the menu is interrupt vector mapping with all of the interrupt vectors and their names. Vector number 8 is TCA0 overflow and low underflow, and we can see the name of our interrupt vector. Returning to MPLABX, we need to include the header for the interrupts, which is AVR AVR/interrupt.h, and then we will include the header for the device file, AVR/IOTN1627, then Control-click to follow, and then Control-F to search. Then we can type in interrupt vector. And we will also see all of the available vectors. Under that, we can see TCA0 interrupt vectors, and corresponding to vector 8, just like in the datasheet, is the overflow and low underflow vectors. I'm just going to copy the full vector name TCA0_OVF_vect and use that in my ISR. Now we need to decide what to do in the ISR. First, I want to toggle the LED on port B, pin 7, so we can do that just like we have in the previous two videos. Then we need to reset the TCA overflow flag so we can reset again. And we do that just like we did in the previous video. TCA0.single.int flags or equals TCA single OVF bit mask. Now we need to call our functions in main and put the CPU to sleep. So in order, I will call our functions main clock control, init ports, init TCA, and init sleep. Then enable global interrupts using the SEI function. Finally, we issue the sleep instruction in the while one loop, so each time it wakes up, it carries out the instructions in the ISR and we put it straight back to sleep. And we do that with the assembler instruction, sleep. And that's it. Don't forget to comment out the header file that we just included to avoid the error attempt to include more than one AVR/IOXXX file. Now program the device and confirm the onboard LED is toggling every 1 second. For the low power measurements, check out the next video in this series where we will modify our Curiosity Nano board to disconnect the onboard power supply so that we can take accurate power measurements.